Hello there, students and friends. Welcome to my new episode of the Back to Basic Physics tutorials, this time involving non-zero net force acting on a rigid body, which is an application of Newton's second law of motion. So just hang on, watch and learn. This is the question. A large crate is suspended from the end of a vertical rope. Question letter A. Is the tension in the rope greater when the crate is at rest or when it's moving upward at constant speed? Question letter B. If the crate is traveling upward, is the tension in the rope greater when the crate is speeding up or when it is slowing down? In each case, explain in terms of Newton's laws of motion. For our answer and explanation to this question, we will first identify the forces acting on the crate. Using this free body diagram, we say that there is an upward tension force exerted by the rope on the crate, and that is represented by the blue arrow pointing upward. This is denoted by capital letter T, which means the tension force. Now, there is also a downward force represented by the red arrow pointing downward, and this represents the force of gravity of the Earth exerted on the crate, which is commonly known as the weight of the crate, W. All right. So our first question is actually uh, asking us in which situation is the tension force greater in magnitude, when it is or when the crate is at rest or when the crate is moving vertically at constant speed. All right. So, according to Newton's first law of motion, also known as the law of inertia, or sometimes called the law of static equilibrium, we say that the vector sum, also known as the net force acting on a body, is equal to zero. All right, when the body is either at rest or when the body is moving at constant speed in a straight line path, meaning constant velocity. All right. So, in other words, the same magnitude of the tension force, okay, in either situation, whether the body is at rest or whether the body is moving at constant speed in a straight line. Now, since the two forces, all right, are opposite in direction, um, we first emphasize that the net force, all right, is just the vector sum of the two forces, all right, the vector force capital T and the vector force small letter w, all right. But considering their magnitudes, we can actually come up with the relationship that the magnitude of the tension force capital T is also equal to the magnitude of the gravitational force or the weight of the crate W. So T is equal to W whether the body is at rest or whether the crate is moving upward with constant speed. All right. Now, for question letter B, which is asking in which situation is the tension force greater? If the crate is speeding up, meaning if it is accelerating in the upward direction, or if the crate is slowing down but still moving upward. All right. So for those two situations, okay, in which situation is the tension force greater? So let's start with the first case. Okay, when the crate is speeding upward, we say speeding upward also means that the body is accelerating in the upward direction. The fact that it is accelerating, all right, it suggests that there is a net force also in the upward direction. According to Newton's second law of motion, the law of acceleration, all right, the body accelerates because it is acted upon by a net force. Okay, and whatever is the direction of the net force will also be the direction of the acceleration. And since we said that the crate is accelerating upward, it means that the net force that causes this acceleration must also be directed upward. And that will only happen if the magnitude of the tension force is greater than the magnitude of the weight. So in our equation, F net equals MA, we have T minus W. All right? T minus W suggests that there is a difference in the amount of force. All right? And that difference in the amount of force between the tension force and the weight W constitute what we call the net force, which causes the body, in this case the crate, to have an upward acceleration, or that the crate speeds up, all right, in the upward direction. So when we isolate capital T, we come up with the derived equation for determining the tension force capital T. All right, it is equal to the mass, all right, multiplied by quantity A plus G, all right, which actually means that the tension force is just equal to the product of the mass and the acceleration, small letter a, of the crate, plus, all right, the mass of the crate multiplied by acceleration due to gravity. We just factored out the mass m and then express it this way, all right, and this suggests that the magnitude of the tension force T is in fact greater than the weight of the crate. Now, the other situation is when the crate is slowing down but moving upward. All right? So, still under Newton's second law, the acceleration is negative. All right? Opposite to the motion of the crate. Okay? The crate is moving upward, but it is being slowed down, meaning the acceleration is negative or directed downward. That means the tension force is also directed downward. Now, a downward net force, okay, happens because uh, it is now the magnitude of the weight W that is greater, all right, greater compared to the magnitude of the tension force T. So our equation now becomes F net equals MA, okay, that is equal to W, or the magnitude of the weight W minus the magnitude of the tension force T, all right, and isolating capital T, or the tension force, we come up with this derived equation for this particular uh, situation. All right. Capital T now becomes, or is equal to, the mass multiplied by quantity G minus A, which means that to get the tension force T, all right, we just subtract the weight mg, okay, minus the mass of the crate and its acceleration, small letter a. So this means that for this particular situation, all right, the tension force T, force exerted by the rope on the crate, happens to be smaller or less than the weight of the crate. All right. So as a final answer to our question, in which case is the tension force greater? All right. When the crate is speeding up, or when the crate is slowing down upward. So our final answer is that the tension force is greater when the crate is speeding upward, as shown by this derived equation for the tension force T, compared to the tension force of the rope on the crate when the crate is slowing downward but moving upward. All right, so for you to be able to fully understand why we came up with this relationship of the force tension, okay, as compared to the weight of the crate, let us quantify, all right? Let us quantify and determine quantitatively, all right, the amount of the force tension T, all right? And we will do that by assuming that the crate has a mass equal to 100 kilogram, all right? So in the case letter A, all right, where the crate is at rest or moving at constant speed or constant velocity. All right, so the working equation for the force tension capital T is just equal to mg. All right, mg being the formula for finding the weight W. So when you substitute, we have 100 kilograms as the mass of the crate times acceleration due to gravity, 9.8 meters per second squared. So we will get the value or the amount of the tension force capital T equal to 980 newtons. So 980 newtons is also the weight of the crate. All right. And for the second case, where the crate is speeding upward or accelerating positively upward, our working equation that we derived earlier for determining the force tension capital T is just equal to the mass multiplied by acceleration due to gravity plus, all right, the acceleration, small letter a of the crate. This time, aside from assuming that the mass of the crate is 100 kilogram, we also assume that the acceleration, small letter a of the crate, all right, is positive 2.0 meters per second squared. This is the case when the crate is speeding upward. All right. So when we substitute in this working equation for capital T, we have 100 kilograms multiplied by the sum of 9.8 meters per second squared and 2.0 meters per second squared, which is 11.8 meters per second squared. All right. And multiplying them, we will get the value or the magnitude of the force tension capital T equal to 1,180 newtons. So this is uh, the amount of the tension force or the magnitude of the tension force when the crate is speeding up with an assumed acceleration of positive 2.0 meters per second squared and an assumed mass of 100 kilogram, which obviously the force capital T or the tension of the rope is a lot greater compared to the weight of the crate. So for the final question, all right, Uh, we're now talking about the second situation where the crate is slowing down but still moving upward. All right, so using still the same assumed mass, 100 kilogram, and assume magnitude of the acceleration equal to 2.0 meter per second squared. Okay, our derived equation for this tension force T when the crate is moving upward but slowing down, we have capital T equal to mass quantity G minus A. So when we substitute, all right, the mass 100 kilogram, okay, to be multiplied by the difference between acceleration due to gravity 9.8 meters per second squared and the assumed acceleration small letter a equal to 2.0 meter per second squared. All right, doing our math, we will get the magnitude of the tension force capital T equal to 780 newtons. So obviously, the tension force that we got here is much less than the amount of tension force that we had earlier in the case where the crate is speeding upward. All right. So that completes our answer to this question. Thank you very much. Till our next episode, inshallah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.